In this video, we will discuss crystal growth. So first I want to introduce what are semiconductors, or what atomic species make semiconductor. So this is a periodic table, and if you look at the right side of the periodic table, you have these non-metal species, and if we just focus on those, there are elements that belong to group 4, and they are silicon and germanium. So here is silicon and here is germanium, and these both make semiconductors. And silicon obviously is the most widely used semiconductor, and these are called the elemental semiconductor because they are made of only one atomic species. You could have a compound semiconductor. For example, if you have a gallium and arsenic and they form gallium arsenide, and this is a compound made of group 3 element and group 5 element, we call that 3,5 compound semiconductor. Another example of 3,5 compound semiconductor is indium phosphide. And gallium arsenide, indium phosphide, and other related compounds make up a very large portion of optoelectronic semiconductors that make optoelectronic devices. You could also have a compound between group 2 element and group 6 element, and for example, zinc selenide is an example of 2,6 compound. Zinc is here and selenium is here. Another example will be cadmium telluride, and that's another example of 2,6 compound semiconductor. So those are the chemical composition of semiconductors. Now, how do we make them? You can grow bulk crystal, large crystal ingot, using several techniques. The most widely used technique is a technique called Czochralski technique. Float zone technique is another widely used technique. So to show how Czochralski growth works, you first take silica, SiO2, which is commonly found in sand. In fact, silicon and oxygen are two elements that are most commonly found, most abundant in Earth crust. So you take silica, and then there's some purification process. There's some purification process as shown here in this flowchart on the left, and you make a melt. So at this stage you make a melt, and that goes in here in this schematic shown here in the middle, and these melt is then put in touch with a very small seed crystal, and the seed crystal is put in contact with melt and slowly pulled up, and as this melt cool down, they crystallized, and they crystallize according to the orientation of your seed crystal, and that's how you grow these big ingot of single crystalline semiconductor material. For compound semiconductor, you use something similar, but you have to be more careful to exclude any atomic species that may seep in from your ambient. So the technique is called the encapsulated Czochralski technique. So here is a figure of the Czochralski growth tower. There's a person here. It's a pretty big tower, and here on the right is a photograph of the ingot of a piece of single crystalline wafer, and you would basically chop. Once you make this ingot, then you would cut these. Then you would cut this into small wafers, and those are typically what we purchase from manufacturers. Now, this is a bulk crystal growth. So you make a big piece of crystal, and another very, very important technology is epitaxy. Epitaxy means growth of crystalline film on a crystalline substrate, and the film then conforms to the substrate, so it grows along the direction of the crystal dictated by your substrate. There are several different types of epitaxy techniques: molecular beam epitaxy, metal organic chemical vapor deposition, liquid phase epitaxy, and atomic layer epitaxy, or more often it's called the atomic layer deposition. All of them are currently in use. Metal organic chemical vapor deposition are very common, and atomic layer deposition also are very commonly used in production of these electronic devices. So here's a schematic of a typical metal organic chemical vapor deposition system, MOCVD system. So basically it's composed of the source. So here you produce, you have a precursor materials and sent into a reaction chamber here, and where you have a substrate typically heated to a high temperature, so that these precursor materials that are delivered will come in contact with the substrate surface, which is at high temperature. Then the thermal energy decompose the precursor materials and leave only the desired element on the surface, and that results in crystal growth on the substrate. So here are some photographs of a typical MOCVD system. You can see that there are many wafers all together, so that it grows. It can grow thin films in large quantity, and these are the various gas lines that are needed to control the flow of precursor materials and carrier gases and other things that are needed. So here is an example of the film that was grown by MOCVD technique. This is a gallium nitride and other related nitride compound thin film grown on a substrate. So you can see a very high quality thin films can be grown by this technique. Another important technique is atomic layer deposition. This technique is originally developed as an epitaxy technique, but nowadays it's more commonly used as just an atomic layer deposition. In other words, the film doesn't really conform to the crystal structure of the substrate. The atomic layer deposition is very similar to chemical vapor deposition. However, it uses a particular chemistry that is self-limiting. So here in this example, the schematic on the left shows the growth of zinc sulfide film, and it uses two different precursor species, zinc chloride and hydrogen sulfide. And first, zinc chloride comes in. When zinc chloride molecule is absorbed on the surface, it forms only one monolayer, and the chemistry is such that any additional molecules that may come in are not chemically bound on the surface. So once they form a one atomic layer, then the reaction stops, and you can then purge any excess molecule that you may have, and then you send in the next precursor, which is in this case hydrogen sulfide, and the hydrogen sulfide then react with the zinc chloride that was formed on the surface, and it leaves zinc and sulfur compound only. And once again, the chemistry limits itself to a one atomic layer, and this process continues to form a high quality zinc sulfide thin film. The advantage of atomic layer deposition is that it can grow a precise thickness, a film with a precise thickness, and also it can deposit film on a very complex geometry. So for example, Here on the right, it shows an electron micrograph showing a highly porous, nanoporous substrate, and we have done a zinc sulfide growth, and actually titanium oxide growth in this case, on this very complex surface, and you can see that despite these complexity, the film is formed highly conformal fashion as shown here, and this is the titania layer deposited by the ALD technique. So ALD technique is now commonly used in the standard CMOS fabrication.